In this video, we're going to look at a mathematical proof technique called mathematical induction. And this is used often to establish a statement that's true for all natural numbers. It tends to be often viewed as like a weaker form of proof, only to the extent that it often doesn't reveal why something works, but it's still a completely legitimate deductive way of reasoning. So, it still works. But it's really useful if you kind of come across a pattern that you think is going to work for all numbers, and maybe proving that directly is just kind of cumbersome and would involve all these different cases. Mathematical induction can be used to show that it's true if you suspect that it is. So the way it works basically is that you break the process down into two steps, and you prove that your statement is true for some base case, and that will often mean that you're going to show that it's true for the first natural number that you're considering. Now, the word first depends on the context and the statement, but it's often zero or 1. And I know 0 is not a natural number, but sometimes we just use that extension. But it could be a higher number. So you show that that statement is true for that first number, and then in the next step you say, well, I'm going to assume it's true for an arbitrary natural number k, bigger than the number in your base case. And if you can show that by assuming that's true, it necessarily implies that the statement is true for the k plus first natural number, then if you combine those two steps, what you've essentially shown is that this statement is true for all natural numbers. All right, and the useful analogy is that it's like a series of dominoes. The base case is analogous to pushing the first domino over, and the inductive step here is you proving that if one domino falls, the next one's going to fall. So the result is that all the dominoes are going to fall. Okay, so let's look at how this proof will be used. So here's a statement that we want to show is true for all natural numbers. Now, the first way I'm going to do it is I'm going to just prove it directly using Gauss's method, which we've come across. So using Gauss's method, the way we would prove this is, so this is not an inductive proof here. We've seen that we can establish the sum to be 2 plus 4 plus 6 plus 8 all the way up to 2n. And we can say that that sum is also the same as writing it in the reverse order. 2n plus 2n minus 2 plus 2n minus 4 all the way down to 2. And by adding those, we'll get double our sum. And every single term here in this double sum is going to be the same. 2n plus 2 plus 2n plus 2 all the way down to 2n plus 2. And if we want to know how many there are, we can kind of go back to the indices, right? This 2 here is really 2 times 1. This 2 is really 2 times 2. This is 2 times 3. So we can see that the third number is a 6. The second is a 4. So this must be the nth number. So there must be n of them. So this is 2s equals n of these dividing by 2. And we can factor out a 2 here in the top, and we see that the claim is true. So that was a direct way of proving this. Let's see how this would look if we were to try to prove it inductively. So I'm going to slide that over there. Okay, so using induction. Okay, now to follow this approach, we need the two steps. The first is the base case. And the base case will be, we need to show that this is true for the first natural number, which would be 1 in this case, since that 2 is really 2 times 1. Okay, so we want to show this statement is true for n equal to 1. Well, let's see. 2 times this 2 here, right? If n equals 1, we're just adding that 2. So 2 equals 2 times 1, which is equal to, so I'm going to put a question mark here. Is that equal to 1 squared plus, oops, I didn't need that second squared. Is that equal to 1 squared plus 1? That is true. So this statement does hold for n equals 1. So now we're going to use the inductive hypothesis here in the inductive step. Okay, so now what we're going to do is we're going to assume this statement holds for n equals k. So what that means, to be very explicit, what that means is we know we can use this fact. So in other words, we can assume that this is true. 2 plus 4 plus 6 plus 8 all the way up to 2k is equal to k squared plus k. We want to show that this implies the statement is true for the next one, for the next natural number after that. So, in other words, we want to show that this is true, that 2 plus 4 plus 6 plus 8 all the way up to 2. Now you got to be careful because the next one would be 2 parentheses k plus 1. We want to show that that's equal to k plus 1 squared plus k plus 1. Okay, so I was very explicit about what we're trying to show just for this first video, at least. All right, just so you get the idea. So what we're going to start with actually is we're going to start with this expression right here, and we want to ultimately show that that equals what we have on the other side of the equal sign. So we take this sum, 2 plus 4 plus 6 plus 8 plus etc. Now I'm going to write out the term right before it, which is 2k plus 2 parentheses k plus 1. All right, now we want to show that that equals this. And what we're going to do right away is we're going to use our inductive hypothesis, which is this statement here. We're assuming it's true for the kth natural number, which means that we can replace that with k squared plus k. So that is k squared plus k. And now I just got this 2 times k plus 1 left. Okay, now our goal is to just see if I can rearrange these terms to make it look like this. And I think if, let's see, I'm just going to expand this out. So this is k squared plus k plus 2k plus 2. Now doing a little scratch work over here on the side, if you do some scratch work here, this expression down here, k plus 1 squared plus k plus 1, that's k squared plus 2k plus 1 plus k plus 1. So that's k squared plus 3k plus 2. And I think that's precisely what we're going to get. That's precisely what we're looking at here in the bottom. So I really just kind of need to reverse this arrangement here. So I'm gonna rewrite this now as k squared plus 2k plus 1 plus k plus 1, and you can check that that is all I've done is sort of breaking up the 2 into 1 plus 1, and rewrote it so that we can clearly show that this is k plus 1 squared plus the quantity k plus 1. And we are done with the proof. So that is what the proof would look like if we did it inductively. You can see why I mentioned earlier that it doesn't exactly show you why something is true, but it is a valid way of showing that it is true. So again, it's useful if you come across a pattern that you think is true. If you prove it inductively, then you will have shown that it's true, even if it doesn't reveal exactly why it's true. I would say Gauss's method there shows why this is true, because it talks about, or at least reveals, how you can sort of pair up these terms in the sums and always get double that entire sum. And, in other words, the structure of it is a little bit more revealing than inductive proof. But there's our first example of an inductive proof, and we'll look at a couple more.